guys, welcome back to another gravitational fields problem on orbits. The orbital radius of one exoplanet is 4.02 times 10 to the 11 meters, with a period of 1090 Earth days. Calculate the mass of the star around which the exoplanet revolves. So I'm going to start this off by drawing a picture, a really simplistic picture, just to get a sense of what's going on. So I've got a star and I've got an exoplanet orbiting in a somewhat circular or elliptical path. Okay, now the distance between the star and the exoplanet is r, the distance between their centers. And they tell us that distance, it's 4.02 times 10 to the 11 meters. Okay, now we're also given the period of the orbit, the amount of time it takes for the exoplanet to make one complete revolution around its star. So capital T is the symbol for period, and that is 1090 days. Now, something that we're not given directly in the problem, but that we know, is the universal gravitational constant, capital G. 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. And the question is asking us for the mass of the star around which the exoplanet revolves. So we're looking for m sub s, or the mass of the star. So the relationship I see here is that there's a planet orbiting around a star. It's exhibiting some kind of centripetal force in between the two objects, and that centripetal force is caused by gravity. You know, because it's a gravitational force not on Earth, we have to use the expression for the universal gravitational formula. Okay, first and foremost, Fg is equal to Fc, so centripetal force is equal to force of gravity, and then force of gravity is G, mass of the exoplanet, mass of the star, divided by the distance between their centers squared, and that's going to be equal to the centripetal force, mass of the exoplanet, times the speed squared divided by the distance between them. Okay, so some nice cancellations happen at this point. We can cancel out this r with one of these, and we can cancel out the mass of the exoplanet with the mass on the left, which is nice because we actually weren't even given that information in the problem. So we need to solve for ms, so we're going to multiply r towards the right, and we're going to divide g down to the bottom here. Okay, so we're going to get ms is equal to v squared r over g. Okay. Now, we don't know what v is, right? We have to find it. So in order to find v, you have to think about the logistics of the problem. V is the speed around which the exoplanet is revolving around its host star. Now that speed, just like in kinematics, we say that speed is equal to distance over time, and that holds true here as well. Speed is distance over time. The distance that the exoplanet travels is a circle, and specifically the circumference of that circle, given by radius r. So delta d is 2 pi r, and the time it takes for it to do one complete revolution, we said, was the period, capital T. So v is equal to 2 pi r over t. Now in the expression I have v squared, so I'm just going to go ahead and solve for v squared. If I square everything, I'm going to end up with 4 pi squared r squared over t squared. Okay, so this is what gets plugged back in here. So ms is equal to 4 pi squared. Now you have r and r squared. When you multiply those two together, they have the same base, so you add the exponents and it becomes r cubed over g times t squared. Okay, so there's one more conversion I need to do, and that is that t in the problem was given to us in days. We have to convert it to seconds. And that's actually a really straightforward step. Okay, so t is equal to 1090 days. And if you remember my hint from many videos ago, in order to convert the unit, you multiply it by 1. But that 1 is a fraction. Now, on the bottom of that fraction, you put the unit you're trying to get rid of, which is days. And I'll say 1 day. And you put the unit you're trying to get on top, seconds. You ask yourself what ratio of seconds to days equals 1. Okay, well, there's 60 seconds in a minute, and 60 minutes in an hour, and 24 hours in 1 day. So 60 times 24 seconds per day. Okay, and when you crank that out, you are going to get t is equal to 9.4176 times 10 to the 7 seconds. So I can plug that right back here, but don't forget that has to get squared. Okay, so moving on, we're going to start plugging in our values. So let's move this up a bit. So now we do ms is equal to 4 pi squared r cubed. R is 4.02 times 10 to the 11 meters cubed divided by 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times time. We just found that, but make sure you end up squaring it in the formula. 9.4176 times 10 to the 7 seconds squared. Okay, so at this point, the most difficult part is entering all this in your calculator without making a mistake. What I would suggest, cube this first, then multiply by 4 times pi squared. Take that number and divide it by this expression in brackets. Okay, when you crank all that out, you are going to end up with the mass of the star, which is 4.3 times 10 to the 30 kilograms, which is about just over twice the mass of our sun. Okay, so that's it for the video, guys. I hope you enjoyed it. If you did, I would encourage you to smash that like button so that I know what I'm doing makes sense to you guys. And other than that, I will catch you tomorrow at 12 noon for video 149, Orbits 3. Alright guys, that's it for this video. I hope you enjoyed it. If you did, be sure to smash that like button so I know what I'm doing makes sense to you guys. And you know how you can stay tuned for my latest videos? By subscribing to Physics in the Flesh. I post every weekday at 12 noon, and this way you guys can always be the first to know when I post a new video. As always, guys, thank you so much for watching. If you missed any of my earlier videos, be sure to click over there on the right. You can click and watch those videos on your screen right now. Anyways, guys, Physics in the Flesh out. Whoop, whoop. Holy crap, my nose looks big on camera. I gotta find a new